Hey geometry team, it is Mr. Zabo, and we are back to some videos. So we're going to start this video. We are in chapter 10. We are starting to talk about the circle, and we're going to do a bunch of introduction stuff today, and then we'll follow it up with a whole bunch of information on many different things about circles. So to get started, I want to talk about what a circle actually is. The definition of a circle is the set of all points in a plane that are a given distance from a point. Okay, what do we mean? Well, we have the center of the circle is a point, and what the circle represents is all of the points that are the same distance away from that in a plane. When we bring it out to 3 dimensions, we're talking about a sphere. So a radius is a segment, and it joins the center to another point that is on the circle. We're going to skip concentric circles for a second and go to what do we mean by on a circle. Well, in this diagram to the right here, points A and O are not on the circle. They are considered to be in the interior of that circle. If point B is not on the circle, that is considered the exterior of the circle. And therefore, point C is on that set of points that is equidistant from the center. And if O is the center of the circle, C is what we talk about when we consider something on a circle. All right, now, concentric circles, what are they? They are 2 or more circles with the same center. So if we look at the diagram on the left, if this is the center, these would be considered concentric circles if they are considered the center of this circle and the center of that bigger circle here. Those 2 circles would be considered concentric. They have to share the center. A few more vocab terms. A chord is also a segment, and it joins any 2 points on the circle. Example, A and D are points that are on this circle, so that segment, AD, is a chord. The diameter, however, is a segment that passes through the center of the circle. So as an example, A passes through P, the center, goes all the way to B. Segment AB would be considered a chord, or a diameter. We'll call it a segment there too. Now, when we talk about distance from the center, we say that a chord is the distance from a center of a circle to a chord, and we measure that always as a perpendicular segment. So if I want the distance from this center to this chord, we're always going to measure that in a perpendicular distance. Perpendicular distance is the straightest, or is the shortest distance between a point and a line, okay? Which gives us 2 theorems. Theorem 74, if a radius is perpendicular to a chord, it's also going to bisect that chord. So if I know I'm given this, I can conclude that chord was bisected. So think of all the different things this could bring up. If I draw a radius, I have a right triangle. If I draw another radius here, I have another right triangle. I have congruent triangles. I can use Pythagorean theorem. All of these things are things that should be starting to go through your mind as we start talking about perpendicularity, we start talking about chords and distance from the center. With theorem 75, we have a radius of a circle given to us, that's this, and it is bisecting a chord. Here's my chord, and I have it already marked as bisecting. Well, what conclusion can we draw? It's perpendicular. So this is the converse of theorem 74. Keeping all these things in mind, and if we recall, jump in the Wayback Machine and recall section 4.4, if 2 points are equidistant from the endpoints of a segment, then those 2 points can determine the perpendicular bisector of that segment. So recall if OA is congruent to OB, DA is congruent to DB, then we know those 2 points determine this perpendicular bisector of segment AB. That can play a role here with our circles and our radius and chord as well. And that's theorem 76. The perpendicular bisector of a chord passes through the center of the circle. And you can see why. If I take this chord and I bisect it perpendicularly, it is nowhere to go but straight through the center to create a radius and then a diameter eventually. So it has to be true. Now, first example we're going to do, and then you guys are going to have a whole bunch of time to work on our homework, is a proof. Okay? And proofs are going to be back. We are going to work on 2-column proofs again here in chapter 10. Not as much as we did during first semester, but we will have some proofs throughout this chapter. So again, my given information is important. I've been given triangle ABC is isosceles with base segment BC. Okay? What conclusions can I draw from that? I don't know how many of these I'm going to need, but I know that segment AB is going to be congruent to segment AC. Okay? I know that angle ABC is going to be congruent to angle ACB. All of that from being isosceles. Now I'm going to just write all these out because I don't know what is or is not necessary yet. That's what I'll put in my statements. I know that I have a circle P and a circle Q. When I put those letters here, that's naming those circles, and that means P and Q are centers of those circles. We don't have to state that in our proof. And we will have to state that we have circles, but we don't have to state that P is the center. As long as we name it circle P, circle Q, that's implying that that point is the center of the circle. Okay. And segment BC is parallel to segment PQ. Well, I've got some interesting information that I'm going to be able to deal with based on that then. And I'm trying to prove that the circles are congruent. Circles are congruent if they have congruent radii. So if I can show that segment PB is congruent to segment QC, and that those are radii of those circles, which I will have to state, then I'm good to go. I have shown that these circles are congruent. Okay? And conversely, if I'm given congruent circles, I can then conclude that those radii are congruent. So take a minute, maybe try to outline what this might look like, and we'll come back and start to break that down. All right, so I got us started here. We're going to need the fact that these angles are congruent. Okay? I don't need this yet. I'm not going to completely erase it though, because it's something that's going to be used and going to be important. But I know my angles are congruent, and I know I have parallel segments. Therefore, I have angle P and angle ABC are congruent. Angle Q and angle ACB are congruent, because parallel lines implies corresponding angles are congruent. You have to state the parallel lines in your reason. A lot of you have been forgetting to state that. Now, I hope you recognize what we have. With these angles now congruent, we have a bigger isosceles triangle. See where that takes you. All right, so hopefully we got to the fact that segment AP must be congruent to segment AQ, because if those base angles are congruent, the sides opposite are congruent. Then go back to my original isosceles triangle. Since the original triangle ABC was isosceles, AB is congruent to AC, and I can use subtraction to get segment BP congruent to segment CQ. We're not quite done yet. There's actually going to be a couple steps left here. First, I never stated that these are circles, and we need to. So we're going to state circle P and circle Q as givens. If I don't state that they're circles with those centers, then these are not radii. And as I was saying that, I caught myself, maybe some of you caught me as well. Instead of restarting it, I figured it'd be a good lesson to talk about that mistake. I never stated that angle P was congruent to angle Q. And that is necessary to get those sides opposite congruent. So step 6, I would actually have to state that angle APQ, or angle P, is congruent to angle AQP, or angle Q. And that's the transitive property, or substitution. Okay. ABC is congruent to APQ, ACB is congruent to AQP, and ABC is congruent to ACB. That's a transitive property. So that's actually not substitution. That's straight transitive because we have 3 congruencies that we are using there. Now I get to the fact that these are circles, and it's circle P and circle Q, which is incredibly important because that puts P and Q at the center, and I have now shown that they are congruent. I can now state circle P is congruent to circle Q because radii congruent implies circle congruent. You don't technically have to state that there are radii. Okay, that is implied since in the image we've named circle P, so we know P is the center, and in the image it goes to the edge. Okay. If there are questions, go ahead and send me an email. There's a bunch of practice problems that I want you guys to work on. Check the Google Calendar in the Google Sheets calendar that has the homework assignment, and go ahead and get that done as soon as you can. A lot of things to think about here, a little bit with proof, and then keep in mind you're going to use a bunch with perpendicular. So there's going to be special right triangle opportunities, Pythagorean theorem opportunities. There could technically even be sine, cosine, and tangent, some trig opportunities here if we wanted to implement that. All the different things that we've seen with right angles and right triangles certainly can be in play. We will continue to build on this as we get through chapter 10.